Welcome to Maths with EJD. In this video, I'll continue to talk about mathematical induction, and the particular question to be handled in this video is this: to prove that 2 raised power n is greater than n for all positive integers, integers. Okay, now, just like I already established, it is good to follow a procedure here. First of all, we have to state the claim. States the claim. The claim here is that 2 raised power n is greater than n for all positive integers. For all positive integers. That is the claim. And then the next thing to do is to work out the base step. So the base step is, you just taking n equals 1. But, for me, I like to take n equals 1 and n equals 2, or I take as many as possible until I get a pattern that is convincing. So at n equals 1, of course, you have 2 raised power 1 greater than 1. Greater than 1. That implies that 2 is greater than 1, which is correct. So with that, we can actually go to the next step, but then I like to take more. So at n equals 2, right, we have 2 raised power 2, which is greater than 2. That implies that 4 is greater than 2. And that is actually a statement of fact that 4 is greater than 2. So for the base step, the claim is correct. So we can say, therefore, the claim is true. The claim is true for the base case. For the base case. So, since that is established, we have to go ahead to talk about the the uh the inductive hypothesis. The inductive hypothesis. This is the stage where you assume the claim is true for K. So you assume the claim is true for n equals K. So all you just do here is to say that is to say that 2 raised to power K is greater than K. That's all you can do at this stage. So then the next stage is where you do the final showdown, which is the inductive step. The inductive step. So this is where you prove. So you want to prove that the claim is true for n equals K plus 1. So what do we do here? It's always better to go from where you stopped, which is about the K, right? Generally speaking, what this would imply is that you want to show that 2 raised power K plus 1 is actually greater than K plus 1. That is what we need to show. But then how do we go? Remember, for the inductive hypothesis, we had it that 2 raised power K is greater than K. So see what happens here. If you multiply both sides by 2, so you have 2 multiplied by 2 raised power K is greater than 2 times K. So here, that is more like 2 raised power 1 times 2 raised power K, and that is greater than 2K. Okay, so that means you have 2 raised power K plus 1, which is greater than 2K. Now, our job here is to show that 2 raised power K plus 1 is greater than K plus 1. And then now we have it that 2 raised power K plus 1 is greater than 2K. So we can get a convincing proof if we are able to show. So now, since 2 raised power K plus 1 is greater than 2K, so now we need to show that the 2 raised power K, that 2 raised power k plus 1 is greater than is actually greater than k plus 1. So we need to show that 2k is greater than k plus 1. That means 2 raised power k plus 1 is greater than 2k. So this should, if this can also be greater than k plus 1, then we have the deal we want, okay? So that's what we want to do finally here. So this is what we need to show next. So I'll just take the green color, right? And then we have to show that 2k is greater than 2k plus 1. And that means we need to show that 2k minus k plus 1 in brackets is actually greater than 0. So that means you have 2k minus k minus 1 is greater than 0. That means you have 2k minus k is k minus 1. That means k minus 1 is greater than 0. Okay? That means k minus 1 is greater than 0. And of course, in essence, that means k is greater than 1. Of course, for k to be greater than 1, right, it simply means that at the inductive hypothesis stage now, at the inductive hypothesis stage, you know, this is what this happens. This is where k is greater than 1. And that is actually true because at the base case, we had already taken n to be 1, we are taking n to be 2. So definitely whatever you have at the inductive hypothesis state cannot be 1 or 2 again. It cannot be the base case. At least it cannot be 1. That one is sure. So, and it is true actually that at the inductive hypothesis state, k is actually greater than 1. And with this, we can conclude the proof. So we can now say, therefore, uh, so we can say, therefore, 2 raised power k plus 1 is greater than k plus 1. And that leads us to the conclusion, right? In conclusion now, we can say that, since the claim, since the claim that since the claim that 2 raised power n is greater than n is true for the base case, for the base case and the inductive case, inductive case and the inductive case, then it is true. Then it is true for all positive integers, for all positive integers n. Okay, so that's simply how all of that goes, so thanks for listening. If you have not subscribed, make sure you do that. Subscribe, press the notification bell, make comments about what you want us to do. Like if you have a problem you want us to solve, a topic you want us to treat, then also like, share, and let it keep spreading to people that will really need this. Thank you so much for coming along. See you in the next video.